So we had the property that each Gaussian is itself very well approximated by a thin spherical shell of some radius. But the important thing was that we took two samples, either in the case that they came from the same component or they came from different components, and we thought about their squared Euclidean distance as the sum of vectors. This A minus B would be the sum of vectors, which are very close to orthogonal. So that allowed us to estimate these quantities and give upper and lower bounds that hold high probability, because we just have that the squared Euclidean distance is the sum of squares of these nearly orthogonal vectors. So we had things like if A comes from the component mu1, the first component, then itself A minus mu1 is a vector which is random on a sphere and will be orthogonal to things like, if another vector comes from the same component, B minus mu1. So those are two things which we can then easily estimate their squared distance. So this was the basic idea, was that we had some threshold, tau, which for the time being we assumed that we knew it because we knew what sigma was. And we said that if we know tau, what we can do is then, based on this distance-based property, that with high probability every pair of samples that comes from the same component is closer together than every pair that come from different components under the separation condition. All we have to do is we have to connect pairs of samples which are within the squared distance of tau, and then lo and behold we just have cliques which correspond to the different samples from the different clusters. And this would work with high probability. This would be a concentration balance. So are there any questions about the statement? This is what we covered last time towards the end. Any questions? So what I ran out of time last time was actually how to get better separation conditions just from this. That actually you can, so this theorem of Aurora and Kanana stated it in a not full generality way. It turns out that for this result, with a bit more work, and that's where the main meat of their paper is, you can get away with things which do not have the same covariance necessarily. But what you can do is if you take some high dimensional mixture of Gaussians, if you take a high dimensional Gaussian and you project it onto some n/2 dimensional randomly chosen space, it turns out that that has the property of making the ellipses, which define the covariance, as being closer to spherical. So in that way, what you actually do is it relies on a lot of isoparametric inequalities to project on the lower dimensional spaces to approximate even a mixture of non-spherical Gaussians by mixtures of things that are close to spherical. But in contrast, when you talk about just spherical mixtures of Gaussians, there's actually a way to, at first glance, this looks like it's another natural barrier. The same way root n looked like the natural barrier of where the spheres are disjoint. This is the natural barrier where the spheres have very little volume in terms of their intersection. So let me state that a little bit more precisely. So, well, I guess let me still state it informally, but with any smaller separation, there will be triples, A prime, and B of samples, where these come from the same component, and this comes from some different component, and yet nevertheless, A minus B will actually be strictly smaller than A minus A prime. So what actually happens is n⁴ really is the threshold for the separation, where beyond that, if you get smaller and smaller separation, then not only do you have this intersection, but that intersection will actually have reasonable volume. So you really will get triples of samples, which distance-based clustering would be confused by, and it would think that A and B are more likely to have come from the same component than A and A prime, even though that's not true. So, but one of the real intuitions here that you can actually improve this distance-based clustering to a separation condition where we replace n by k. So in the case of mixtures of two Gaussians, it's not n to the 1/4 separation, it's some constant to the 1/4. So the intuition is that, you remember I gave you this thought experiment of, what type of separation are the components almost statistically disjoint? Well, the point is that looking at just the high dimensional distances, we're using a lot of the directions where the components are not actually separated. So actually the separation is being, the directions which they actually are separated in is being overwhelmed by the noise of the orthogonal directions. So the idea is that if we can identify the span of the means, then we can actually find which lower dimensional space is actually the right one to look at distances in and ignore this extraneous thing that swamps our distance-based approach. So that's what we're going to do right now. It's a very simple idea, but it's a powerful one. Does anyone have any questions about this? About the intuition behind this? So let's do this. So, sorry.
What if we set this here? What if it was like the number of common neighbors between two? Like if we have some threshold, we consider someone a neighbor if it's below the threshold, and we consider a number of common neighbors, that even though there might be like a constant fraction.
So that's a good question. Something like that could potentially help you work with a bit better than n to the 1/4 separation. Let's say n to the 0.24 or something like this. But what we're aiming for right now is a separation which is independent of the ambient dimension, other than this root log, which is kind of necessary because we're going to have to take the polynomial number of samples. But as soon as you go to some separation, which depends on k, and k is like 2 in a lot of the settings, then the issue is that the two components will be quite, if you look at this distance-based comparison, the pairs which are closer than other ones will be only just a little bit, like a hair more likely to actually come from the same component. So when you actually cluster that way, you're getting a very biased view of the samples from one of the components, and you're sort of mixing in a ton of other samples from the other one. So the distance-based approaches really are sort of dead in trying to get the types of separation that we're going to aim for right now, at least without projecting to the right lower dimensional space. So that's a good question. Any other questions? So what we're going to talk about is an approach of Impala and Wan. Let me state the theorem, and then we're going to prove it. Unlike the Aurora-Kananga result, this really will be very crucially dependent on the assumption that they're spherical mixtures, and it will not be true without this condition. So that's something to really keep in mind, is that we're getting much stronger separation conditions, but at a very steep cost in the generality. So there's a polytime algorithm to learn mixtures of spherical Gaussians moreover, they even have to have the same covariance in order for this approach to work, which is anyways the setting where we analyze the Aurora-Kananga result. And the separation condition we're going to need now is just mu I minus mu j is at least k to the 1/4 sigma root log. So we're swapping out an n for a k at the expense of restricting to spherical Gaussians with the same covariance. So in fact, this is a pretty easy proof. So let me just need a few lines to do this. So the main idea for this is that principal component analysis is actually going to find the span of the means. Can anyone give me any intuition for why principal component analysis might be able to find the span of the means? I'm going to prove it, but anyone have any intuition?
Well, if it minimizes the square length of projections down to a subspace, I guess, then you imagine that it'll, like if you did a one-dimensional principal component analysis, you imagine that you'd pick up both means because you're minimizing the some of the square projections with each of them, and that will probably hold it.
Yeah, I think that's good intuition. Let me reformulate that intuition slightly, which is that a mixture of spherical Gaussians, which have the same covariance, you can really think about it as taking a random sample, which first, the sum of two independent random variables, one of which selects the mean, and one of which adds the Gaussian noise. So the Gaussian noise is something which is very well behaved in all directions. We know what its variance looks like in all directions, and the first variable is only going to contribute in the span of the means. So that's the intuition, is that for mixtures of the same component, we can decompose them in nicer ways into thinking about our sampling process, and PCA is going to be easy to analyze in this case. So the idea is, let's make this precise. So I'm going to let M be the covariance. Where X is sampled from this mixture of Gaussians, and moreover, zoom this 1 second. Right. So now the main idea, the thing that we want to prove, is we want to prove that let's let U1 to UK be the top K singular vectors. And what we want to prove is actually that span of mu1 to UK is equal to span of u1 to UK provided, let's say, that the means mu1 to UK are linearly independent. And each mixing weight is non-zero. So can anyone tell me, if we have this claim, it'll be a simple proof, why should we be done? Why should this claim immediately imply that we can improve the separation condition from the Aurora and Canaan result? What would our algorithm be? Any thoughts?
Sample, well, take a lot of samples and then try to estimate the top K singular vectors and then just work on that.
Yeah, exactly. So the main point is, we can estimate this. We get good enough estimates to this. Remember that, as we converge entry-wise to what the true covariance matrix is, its singular value decomposition is going to converge to the right one. I mean, you have to, work out a few of the, dot the i's and cross the t's in this, but, then you're going to find good estimates of the top K singular vectors, which gives you roughly the span of the means. The point is that when we project into this space, we no longer have a mixture of k Gaussians in n dimensions. We have a mixture of k Gaussians in k dimensions. So we can actually just black box apply the Aurora and Canaan result. Is that just allows us to replace n with k here. The only catch is that I can't replace every n with k, because I still need this sort of logarithmic dependence on n, because I need that with high probability, when I take some polynomial in n samples, that all of my samples get clustered correctly. So it allows you to replace the actual dominant term in the separation by k, but you still need some very weak dependence on n to make sure that you can take some poly in n samples and get all of them right. So that's the main intuition. But let's prove this claim. Pretty simple claim to prove. So we take x, as I described, as the sum of two random variables, where C is mu1 with probability W1, the first mixing weight, mu2 with probability W2, and so on. And we take Z then to be sampled from a normal with zero mean, sigma squared variance. And the claim is that a random sample X from the mixture of k Gaussians really is a sample from this model where C and Z are independent random variables. So the point is that in this really nice type of mixture of Gaussians, well, actually the components are all identical, so I'm just thinking about a random variable as which of the components I'm choosing for my center, and then what I add for the Gaussian noise doesn't actually depend on which of the components I've chosen. So that's a very, very strong property, but it's something that allows you to get much stronger separation guarantees. So now what we can do, so we have that C and Z are independent. And if I look at the expectation of XX transpose, so I take this empirical covariance matrix, all I end up getting is the expectation of CC transpose plus the expectation of ZZ transpose, because C and Z are independent and Z is a zero mean random variable, right? And this quantity right here, it's early in the morning, someone tell me what this is. So I know you guys are awake. What is this term?
Sigma squared.
Sigma squared I. Sigma squared I. Now this term right here also has a nice explanation, which is, someone tell me what this is? Just easy questions in the morning.
Some of the weighted means.
Yes.
Squared.
Exactly, right? So it's the weighted sum of mu I transpose. Okay? So this is our representation now. And what you can see is, imagine, so this is the matrix, which I'm going to assume I'm given exact access to. In reality, I need to take samples and say that I have a close enough estimate. All these things work out. But if I think about taking this matrix M, and I think about taking quadratic form on this matrix, when I take a quadratic form which is orthogonal to all of the mu's, I get no contribution from this term, and I get a sigma squared from this term. But as soon as I take a quadratic form which actually involves the mu's, I still get my sigma squared here, but I also get some more contribution from here. So that's the intuition, and you can actually make this more precise now. So what you would actually do is you can use the following variational characterization, which we actually covered first day of classes, where we take the k plus first, singular value m. You can actually think about it as the following game. It's just the first player chooses some subspace V of dimension k, and the second player chooses some vector that's perpendicular to V, and you just look at the quadratic form on M. Right? So you can think about this as, in the case where k equals 0 and you're looking at the top singular value, the first player does nothing, and the second player gets to choose any vector, and it's just the largest quadratic form you can get on M over unit vectors. And then sigma 2 is what the other player would do is they'd rule out the span of the top singular vector, that's the best that they can do, and force you to work in the rest, which the best you can do then is to choose the second largest singular vector, and so on. So this is what's called the variational characterization of singular values. And now, in good shape, so now we're in good shape because it follows that, for example, sigma k plus 1 of M, sigma k plus 2 of M, and so on, are all sigma squared, right? Because in this game, what I would do is if I were the first person choosing this min, I would choose the subspace, which is spanned by the means. And I would force you to work outside of that set. Anytime you take some vector that's perpendicular to this set, you get no contribution from this term, and all you get is your sigma squared. So hence what this variational characterization tells us is that everything below this is sigma squared. And what I just argued is actually that if you have a singular value sigma k or anything above it, then actually, there's no way for the adversary to get rid of all of your contribution from this term. All he can do is he can rule out a k minus 1 dimensional subspace. And by the assumption that these means are independent and the mixing weights are independent, I'll always be able to find, whatever remaining vector I have in the span of the top k, mu1 to mu k, I'll still get some non-zero contribution from this guy. So it follows also from the variational characterization that sigma 1 of M, sigma 2 of M, and so on, all the way up to sigma k of M, are actually strictly greater than sigma squared. Now, to actually get the full algorithm, I need to actually say something quantitatively about how much larger than sigma squared they are, because that influences to what accuracy I need to estimate M and how many samples I need. But this is the basic idea. So you can, for mixtures of spherical Gaussians, you can just replace separation of N with separation by K. So are there any questions about this? All right, but what I promised to do today is I promised to move beyond clustering. So that's what we're going to do. So this is good separation because it only depends on K. So for a mixture of two Gaussians, we're still in the setting where the separation is polylogarithmic. But actually, it'll turn out that there are ways that we can learn the parameters of mixtures of Gaussians, even without clustering and even without assuming that the total variation distance between the two components is close to 1. So we're going to do that. It'll take a little bit of time, but there are basically two pieces to this. So what we're going to do is let's work with high-dimensional mixtures of two Gaussians. And the goal is going to be to estimate the parameters to say plus or minus epsilon up to the usual relabeling. Because you don't know which component is component 1 and component 2, so a lot of times we've had to state these laborious types of guarantees. We're really saying we learn a setting of parameters so that there's a matching of our parameters to true parameters across which we get everything right. The means, the covariances, and the mixing rates. So that's our goal. And actually the only assumptions that we're going to work with in this are we're going to need that the mixing weight W1 is bounded away from 0 and 1, just so that you do get samples from the two components. You could put any power of epsilon here and here that you want. It doesn't really matter. But you need some sort of quantitative guarantee to say that when you take a polynomial number of samples, you're likely to see both of the two components. Now, there's another condition we need, which is that the two components are not identical. So we're also going to assume that the total variation distance between the two components is itself at least some epsilon. You can put in epsilon to the 100, epsilon to the 100, epsilon to the 100. It doesn't really change things. But see here, this is a guarantee that we need to sample from both of the two components. This is a guarantee that we need to sample something that is in one component and not the other. So you think about all of the guarantees we've been working with so far, they assume at the very least whatever their separation condition is, they assume implicitly that the total variation distance is actually 1 minus little o of 1. In fact, 1 minus 1 over polyon n, because you need to be able to take some polynomial number of samples and not have any confusion about where the different samples came from. But I mentioned this briefly at the very beginning of this unit, that separation conditions are really only one way to even enforce total variation as a constraint. So you remember that there was this example I gave of a mixture of two Gaussians with no separation condition, that nevertheless the components have very large statistical distance from each other. So actually, we're even going to be able to work with mixtures where the components are just barely different from each other, instead of being almost entirely different. So that's what we'll be able to do. The first work that did this, there's been a few of them at this point, but was for mixtures of two Gaussians. And there was some later work on mixtures of more Gaussians. And there were even approaches based on tensor decompositions that I'm going to cover after we talk about all these things. But the basic idea in this paper is the following plan, which we're going to realize the first part of the plan today, is to reduce the n-dimensional learning problem to a sequence of one-dimensional problems. And the second part of this plan, which we're going to cover next time, is we're going to give an algorithm for the one-dimensional problem with no separation. So no condition that the components are disjoint. Will allow them to be almost entirely overlapping. We'll just need a lower bound, any lower bound, on that the components aren't exactly the same. And that'll be enough to actually revisit Pearson's problem and get algorithms in the one-dimensional case. So these are very disjoint parts of the problem. We're going to cover the first part today, and we're going to assume the second part. And the second part, actually, that's where we'll see some surprising uses of the heat equation, and also later an interpretation of that through algebraic geometry. So that's the roadmap for going forward. But the first thing that I want to describe is really, in this type of setting where the components are almost entirely overlapping, if we had an algorithm for the one-dimensional problem, how could we turn that into an algorithm for the high-dimensional problem? So that's the goal. So are there any questions? All right, so let me tell you, I'm going to work up towards what this algorithm is, how to actually accomplish step one, and then, building on step two, how that would solve the problem. Well, actually, the basic idea is, so we're going to be in the setting where we're going to allow general mixtures of two Gaussians, f of x equals, w1, mu1 sigma 1 x plus 1 minus w1 mu2 sigma 2 x. So we're no longer in the spherical mixture Gaussians. In fact, the components aren't even the same. So it's no longer true that we can think about x as being the sum of two independent random variables in the same way that we exploited when we talked about principal component analysis. But the main idea is just the following claim. This is what the algorithm at a high level rests on. It's a very simple observation, but it's the building block of all of this, is that if we take some direction r and we project samples from f of x. So what I mean by this is that we take x from f of x, and then we map that to r transpose times x, where r is a unit vector. So we just take r and we use it to project our high-dimensional mixture of Gaussians. Then what we should get out is a mixture of two Gaussians too, right? But in one dimension. So the key point is that actually not only does it yield a mixture of two Gaussians in one dimension, it yields a mixture in which we can explicitly write out what its parameters would be in terms of the parameters we don't know. So the key point in this claim is just that the projection of a Gaussian is a Gaussian. That's all this is relying on. It's something that you already know to be true when the Gaussian is spherical, because remember that the spherical Gaussian just has independent components along different directions and is rotationally invariant. So when you project a spherical Gaussian with unit covariance that just has I covariance, then all you end up getting in one dimension, regardless of what you project on, is actually the standard Gaussian, n of 0, 1. But in fact, more generally, when you take any high-dimensional Gaussian, then you can see just by, you can do the same, you can explicitly work out this claim, or you can think about it as if you know the projection of a Gaussian is a Gaussian, then what should the mean of that Gaussian be? It's easy to see that it should be R transpose mu1 in this case. And what should the covariance be? It's also easy to see that it should be R, the quadratic form of R on sigma 1. So are there any questions about this claim? Does it make sense? Yeah? All right, so now we can go ahead with the plan, right? Because the idea is that when we, if we had accomplished step 2, if we had an algorithm for learning mixtures of two Gaussians without a separation condition, which we don't have yet, and we'll have to get to that later, that's a whole other story, then what this means is Well, we could take f of x and we could project it on many different directions. And each of the parameters that we learn, we can think about as giving us linear constraints on the parameters, the high dimensional mixture. When I know, for example, R transpose mu1, that gives me a linear constraint. I know what that value is, and I know what R is. The same is even true for the covariance. If I know what this covariance is, and R is known, then this is just the linear function of this unknown covariance matrix sigma 1. Now, there's a slight issue with sort of realizing this plan, which is we're going to have to project onto many different directions, and ultimately we have to pair up the components across the different directions, right? So let me state that more precisely. But you know, this paper is a bit involved, so I'm probably not going to prove all the details, but I want to at least convince you about the high-level ideas. Okay, so what we're going to assume, you know, what we will prove for step 2, and we'll do this later, is the following. So this is the thing that we're going to assume today. So given samples from a univariate mixture. So I apologize, this will be different, you know, these will be the univariate versions of the parameters, but let me just state the theorem this way. So here, for example, by mu1, this is just the real value, it's just the scalar value because I'm in one dimension. And they have the property that the mixing weight is between epsilon and 1 minus epsilon. And we've normalized it so that the expectation of x is zero, and the expectation of, you know, x squared is 1. So let me just put it in a standard form where the mean is 0 and the variance is 1. Then the key point is we have the following type of separation on the parameters. mu1 minus mu2 plus sigma 1 squared minus sigma 2 squared is at least epsilon. Then there is a polytime algorithm with polysample complexity. To learn the parameters within plus minus epsilon. In fact, you can put you know, even an epsilon to the 100 here, epsilon to the 100 here and here. This doesn't matter. So this you should think of like the an analog of this total variation distance constraint that we have. You see, if my goal is to learn the mixing weights, if the two components were exactly the same, then I'd be in a lot of trouble, right? Because I could potentially the two components could be the same, at least when I take not too many samples. And then I'd never be able to figure out what this mixing weight is. It could be anything, in this range from epsilon to 1 minus epsilon. So you should think of this like an analogy that, if you can project down to one dimension and you have any sort of separation condition, either the means are separated or the variance are separated, even by an epsilon to the 100, then what you can end up getting is a polytime and sample complexity algorithm to learn all of the parameters, the mixing weight and the means and variances, all within a plus minus epsilon. So this is what we're going to be assuming. It's sort of the one-dimensional analog of what we're trying to bootstrap this to get in the high-dimensional case. But let's use this now along with this claim. So now, I want to work up towards this algorithm. I told you that there's a pairing problem. Right? So let's suppose we project a high-dimensional mixture onto two directions, R and R prime. And let's say that we get some parameters, mu a bar, let's say w bar a bar, squared bar, and some other setting of the parameters. So this is when we project onto some direction R, and we invoke this univariate learning algorithm. Let's say it spits out these 5 parameters. It says these are plus minus epsilon, good estimates of the underlying parameters that you wanted to get. And now you also do it for some direction R prime, and you get a different set of parameters. And here what I've done is I've put subscripts for A and B to emphasize the fact that we don't know which one is component 1 and which one's component 2. So you have an issue now, right, that we know that for mu A bar, it equals R transpose mu I, and sigma bar A squared equals R transpose sigma I R for some I, either 1 or 2. Okay? And the same thing is true now for mu hat A, is that we have that it's R prime transpose mu I. Actually, let me write J here to emphasize this. And we also know that sigma A squared is itself R prime transpose sigma J R prime for some J, 1 or 2. So when we take this mixture, we can look at these 2 parameters, and we can interpret them as linear constraints on one of the 2 high-dimensional Gaussians. The same thing is true when we look at this other projection, but the issue is at the end of the day, we want to set up for each of the components on in the mixture, component 1 and component 2, we want to set up some linear system that we can back solve for the high-dimensional parameters. But the issue is that if we mix constraints that come from different Gaussians, we're going to get an inconsistent system, right? So pictorially, just to draw this out, let me show you what's going on here. Let me strain my board drawing abilities. So we have 2 directions R and R prime. And what happens is our univariate algorithm spits out some mixture of 2 Gaussians on R prime, and it spits out some mixture of 2 Gaussians on R. And the bigger issue is we want to pair up which components come from the same high-dimensional mixture, because in that way we can figure out what is the right consistent linear system to create for the high-dimensional parameters. Now it turns out there's one setting where I can actually pair up the components really easily. And it's sort of a quick hack that works, and let's do that. And then I'll tell you more generally how you can do this. Anyone see a quick hack for how we can pair up these different components and the different projections? So the high-level point is that we want to learn these high-dimensional parameters, and we definitely need to project it on many different directions to hope to do that. So just projecting it on one direction is only going to give us a bit of information. We want to piece together the different bits so that they all are about the same component. So is there a hand for an idea about how to pair it up? Give me a dumb way to pair it up so that we can just move on.
Maybe if WA is significantly different from one,
Yeah.
you can just see whether you take the small one compared to the
Yeah,
small
exactly.
one.
I mean, I've learned the estimates, up to an additive epsilon, any epsilon to the constant that I want. So one, simple fix for this pairing idea, which is all I'm really going to cover here because I don't want to get into, more of the details, is the pairing approach here. It's just that if W1 is not just bounded between epsilon and 1 minus epsilon, but rather epsilon and a half minus epsilon, then the point is that the parameters I've learned are provably close to true parameters. So I'll know whether A corresponds to 1 or 2, whether it corresponds to the first or second component, just based on whether or not it's above a half. So if this is true, then matching is easy. And the proof is just a one-line proof, right? Is that either W bar A minus W1 is less than epsilon, or W bar A minus the other mixing weight is less than epsilon, but not both. So when you think about two different estimates, WA and W bar A and W hat A, they'll only be close to each other. There'll only be one pairing of them which they're close to each other. They'll either be close to each other within an epsilon, or they'll be within 2 epsilon, or they'll be close to 1 minus the other one. So you can just pair them up. I guess let me state this a little more precisely, but you just pair up WA bar with the other parameters that you have. And these guys are matched with WA hat sigma A hat squared, if and only if both W bar A and W hat A are less than a half. And that's the proof, right? Now there's a reason that I actually don't like this version of pairing. It's because all the other conditions that we had for these assumptions here were things that we really did need. If we were going to learn the parameters of the mixture, then we definitely need to get samples from each of the two components. And if we want to learn the mixing weight, we definitely have to get samples from the non-overlap region between the two components. They can overlap almost entirely, but when we take one of our epsilon samples, we have to get something that's in one but not the other. Otherwise, we'd have no hope of estimating the mixing weight. This type of condition is not something that you actually need on the mixture, provably. It actually turns out there's a much, much more complicated way that you can get around this. Because if you think about it, as I sweep from R to R prime, actually the parameters change continuously, right? You can think about that just based on that claim about what the projection of a mixture of two Gaussians is that as you sweep R, from R to R prime, actually those parameters change continuously, and that gives you a way to match these things up. So I won't go into more details on that, but these are all in the notes, so you can check out how to remove this type of condition for pairing if you want. but let's move on. I like this quick dirty fix a little bit better anyways. So at the end of the day, now to try and, are there any questions about this? All right, so there's one last thing that we need to talk about to sort of describe what this algorithm is. So in any case, however you do the matching, whether you do it with the quick fix way, or you use things like the continuity of the parameters to try and do the matching, at the end of the day, what we're given is now let's say we look at the first component, and let me call its parameters mu and sigma to avoid having subscripts. Then what we have is we have a collection of linear constraints on its parameters. So we have some set of directions r, which each time we know what r is, we have mu hat r and sigma hat squared r for some r. And you can think of this as just some polynomial number of directions that we've chosen randomly, and we figured out what the projection of the first component is. So keep in mind, the idea is that when we project on one dimension, we have a univariate learning algorithm. We're finding the two components, we're disentangling the Gaussians, then we're matching them up. But it really means that in our high dimensional thing, we have just one Gaussian, and we have many of its projections on all sorts of different directions. And all we want to reason about is why good estimates to these parameters yield good estimates to the high dimensional parameters. Right? And we have the guarantee just that for all r transpose times mu minus mu hat r is at most epsilon, and r transpose sigma r minus sigma hat squared r is at most epsilon. So this is our guarantee. And now the main lemma, unfortunately the proofs of these things are longer than I'd like them to be, is if we choose n squared log n directions r uniformly at random, then the following linear system, which I'm really going to describe it as the least squares optimization problem, which is what you'd really solve, is you look for the mu and sigma, the high dimensional parameters, which summed over all r have the smallest deviation. So remember that when we talked about solving linear systems, it was really the condition number that governed how much errors in your estimates, which these are the constraints. So these are the b vectors in my linear system. So these are the right-hand side. Well, how much the errors in those vectors, in those estimates, propagate to errors in your solution is governed by the condition number. So what this lemma is really saying is just the intuitive statement that this inverse problem is well posed. there's an issue that if the directions were really, really close together, even if the linear system were invertible, it would be poorly conditioned, right? Because all the directions are somewhat close to redundant. You can think about, how the parameters change. If you barely move, they don't change that much. But if you think about taking directions randomly, then the linear system is actually fairly well behaved in how well you can solve its inverse problems. So let me write this out, though, as a linear system, just so that make sure we're on the same page. I'm going to call this star, but any questions about the lemma statement? No questions? All right. So you can actually think about this as we can think of it as the following type of least squares problem. We're going to take a block matrix, and what's going to happen is we have zeros here, but these will be the different directions R transpose, will be the different rows in this matrix. And the rows over here will just be the vectorizations of R transpose. So you think about what the linear constraint you have on sigma is, that's really the inner product with sigma as a vector with R transpose as a vector. That's exactly what you get from this quadratic form. And you have this vector of parameters mu, and then you have the vectorization of sigma. And what you're requiring is that this be close to mu hat R, sigma hat R squared. And you're trying to solve this least squares problem over mu and sigma. So what we're really saying is that this matrix A is actually with high probability, well conditioned. So if you think about things like this submatrix is definitely well conditioned because you're just choosing a bunch of random vectors. So it's something that behaves very nicely. These are also just slightly correlated random vectors, but it also behaves quite nicely. And this is where you get the types of condition number bounds. But at the end of the day, let me state the full algorithm now.
So razors are terrible.
All right, so now this is the full learning algorithm. It's really learning, I guess, without clustering. It's just a natural thing of putting the pieces together. So all we do is we choose n squared log n, directions R, uniformly at random. We haven't solved 2 yet, this problem of returning to Pearson's original question and trying to solve the univariate problem without separation. But I'm going to assert that we can do this now. So we learn the parameters. project this high dimensional mixture onto one direction. And then all we do is we match up the components. So one way is using mixing weights. Or other approaches, which I'll just state, that relying on things like the continuity of the parameters as you sweep from R to R prime. There are other ways to do that without that assumption. And then all you do is you solve the least squares problem, star. You solve it using all of the constraints you got for the first component to get the first set of parameters. And you also solve it using a different, constraint vector for the mean and covariance of the other Gaussian. And the point is that this univariate learning algorithm, I can ask for any sort of accuracy I want. So really, I'm going to learn the parameters up to some additive, epsilon over n squared type of thing. Enough so that all of my estimates are so close, or are at this inverse Pauli closeness, the true parameters, that even when I blow them up by the condition number, I still get the guarantee that the output estimates I have are epsilon close to true parameters, just by virtue of the fact that the constraints on this linear system are not too perturbed. So this is the algorithm. There's actually one thing that I haven't really told you about yet. So there's one missing ingredient. Anyone know what the missing ingredient is besides the univariate learning algorithm? Oh, that's a big missing ingredient that we definitely will not talk about in class. But it's actually related. The issue, the thing that I haven't talked about in this is actually what goes the most wrong when you talk about mixtures of more than two Gaussians.
What did he say? I didn't hear.
Mixtures of K Gaussians, the extension to K. So that I haven't really talked about, but actually, the other thing that I'm not going to talk about, there's a couple hundred, there's a lot of pages in these papers, so let me leave it at that. But the remaining missing ingredient, which is we want to prove that when you project onto R this mixture of two Gaussians, then with high probability, the univariate parameters are not too close. So remember that this univariate learning algorithm we had, it was the natural extension of what was happening in high dimensions, that you need the mixing weights are between epsilon or 1 minus epsilon. That doesn't change when you project things. But the other thing that you needed was that the two Gaussians don't accidentally collapse on top of each other. Because if they did, you really wouldn't have a hope of learning something like their mixing weight well. So there's actually a very subtle but big issue, is that we started off with the assumptions that in high dimensions, the mixing weights are between epsilon and 1 minus epsilon. And also in high dimensions, the total variation distance between the first and second component is at least some epsilon. They're not entirely overlapping. And what you need to prove is that the total variation distance between the projections onto R of the first component and the projection onto R the second component is at least some sort of epsilon, polynomial and epsilon and 1 over n. But they have non-negligible separation distance. Yep?
Would it depend on the dimensions?
It does depend on the dimension, yeah. I can give you a little bit of intuition for this, but I'm not going to prove this. It's a bit laborious to prove it. But the basic intuition for this is that if you think about what this total variation distance is, well, I just need some non-negligible difference in their total variation, some lower bound for it. So if you think about this high-dimensional mixture, what you can do is you can think about it as really a two-case analysis. Of this is that you can look at mu1 minus mu2. So as soon as you have mu1 and mu2 are non-negligibly different from each other, then what's going to happen is we know what their projected difference in their means is. All we would do is we would take this vector mu1 minus mu2, and we take its inner product with r. So when we have some vector of some known norm in high dimensions, we know exactly what happens to the norm when we project it. You just divide by root n, roughly. So in that case, as soon as you have any separation between the means, you're in good shape. Now there's a bigger issue, which is that what can go wrong if, let's say mu1 equals mu2, it still could be the case that two Gaussians have non-negligible statistical distance from each other, even though it's not due to the difference in their means. But this would mean that sigma 1 and sigma 2 are noticeably different. And what's going to happen then is that the difference in their total variation distance is due to their difference in projected variance. So if you think about it as, as soon as you have a lower bound on the total variation distance of component 1 to component 2, either that's due to the difference in their means, which, analyze in a very simple way, or if their means are extremely close, the only way that that can be is if in a typical direction, the covariance looks slightly different. And that actually you can analyze and show that what this means is for a typical direction R, you're also likely to have a lower bound on the difference in their projected variance. So all of this becomes very complicated because the pieces that you need to put together are you need that each of these things are sort of anti-concentrated, and that with some reasonable probability, they're all not too small, so that you can run the univariate learning algorithm with some extremely fine precision based on whatever you prove in this lemma is. Then you can do matching and then solve this linear system and get provably good estimates of the high-dimensional parameters. So these are all the pieces of the analysis, and we haven't even done the univariate case. But the important thing is that the parameters converge to the right ones at an inverse poly rate. Now something goes really, really wrong when you have mixtures of three Gaussians, and I'm just going to sketch this is just for posterity's sake, is that in this case analysis, when we think about three Gaussians, the issue is that I could have a mixture of Gaussians that looks like this. Imagine I have one large component, so this entire overall mixture is pretty well behaved, it has good variance in all its directions, and yet there are two extremely close by narrow Gaussians. They can be very close to each other and still have good statistical distance, but the issue is when you project them onto different directions, actually what's going to happen is you're going to see only a mixture of two Gaussians. It could be extremely close to a mixture of two Gaussians. So ultimately the strategy in this later paper was to project on many directions, in this case learn a mixture of two Gaussians, and then what's going to happen is you learn some mixture of two Gaussians, but you can use the fact that you found a very narrow variance component to project the mixture onto that direction, to cluster out the two Gaussians and then recurse. So in fact, what you're doing is a case analysis that either you'll discover a direction where it looks like a mixture of three Gaussians, and then you can do your univariate learning algorithms and boost up into this high dimensional thing, or you're going to be fooled into thinking it's a mixture of two Gaussians. You're going to learn some mixture of two Gaussians, but by virtue of their parameters being close, you're going to have found some very thin direction that you can then use to project and make progress. If you think about projecting out this pair of mixtures, you can then put it in isotropic position and stretch it out in the direction where they are separated. So it becomes, and I'm not going to do that to you, so we'll stop there. But
So how does it depend on K?
so it's exponential in K. The quirk is, so we're going to see that in the univariate case, when we just analyze mixtures of two Gaussians, we're going to analyze Pearson's approach. We're going to show 6 moments work. Then for mixtures of K, you need theta of K moments. In fact, in one dimension, there are mixtures of K Gaussians that are different mixtures, but are exponential in K close. So in a sense, parameter estimation is actually limited by exactly that type of bound. The funny thing is, when we then talk about the algebraic geometry approach, the ironic thing is it tells you there's a finite time algorithm, but it doesn't tell you provably what that finite value is, because it uses some non-constructive properties of systems of polynomials. So it'll say there's a finite bound, and that ends up going in the exponent, but it provably doesn't tell you what that finite bound is. So I'll leave that as a mystery, but we'll see that.
Do any of these algorithms have a way of learning how many Gaussians to look for?
Yeah, so again, stuff I'm not going to cover, but if your goal is just to learn a mixture of Gaussians, that really is a mixture of Gaussians that's close to the true mixture, but not even having its parameters close, you can actually black box use an algorithm like the one I described right now for learning the parameters to get rid of the mixing weight assumption. Because what you would do is you just do a 2-case analysis, right? So either the mixing weights are in the total variation is lower bounded, or it's well approximated by 1 Gaussian. So in that case, you do either or, you do hypothesis testing, and you decide, you find one of them that's close, but it actually doesn't answer the question of, you're not for sure guaranteed about having the right number of components in that situation. All you're guaranteed is that you have a proper mixture of, at most, your upper bound of the number of components, which is close. So actually the lower bound that we'll talk about later for even the one-dimensional problem is exactly, you can't tell apart 1 Gaussian from a mixture of K Gaussians that looks exponential in K close. And it'll be related to the comb function. So that was the thing that we used for the spikes and sine. So it'll be same types of tools, but until next time. I guess turn in your homework. And the other announcement is, so I'm going to create, for those of you who've talked to me about projects, great. If you have your own idea, that's awesome. If you don't, I'm going to be putting up probably tomorrow a list of suggested projects with some details. I think it's better if you try and find someone to work with if you haven't already who might be interested in it. It'll be first come, first serve, but on that sheet, I'll also put up the parameters of what I want in terms of, I think it'll probably be around a 4 to 6 page essay. But what my expectations will be for doing new research versus doing a literature review will be different. So I'll describe that in detail. So check it out tomorrow, and I'll send out an email when it's up.
Should I be concerned if I have no enough?
How many did you not get? About half. All right, let's chat. Well, you shouldn't be concerned, but you should try and, you should try and